Hello, everyone. Welcome for another day in the IEEE PSYP Summit, United States and Canada. My name is Conor Schmidt. I'm currently the IEEE PSYP Technical Activities Coordination Committee Coordinator. And it's a great pleasure for me to be your host here today. We have 3 sessions over the day. As you can see in the flyer here, our first session is a keynote speech with David Koehler. After that, we have track number 3, which is going to be in a different link. And by the end, we have track number 4, which is going to be provided by a different link, which is going to be a Zoom session, as is more a network. So if you register in these sessions, you're going to be receiving the link on your email, or also the link to join is available in the WhatsApp group. But regarding the session that we are going to host right now, we have this special session with David Koehler on the theme of condition assessment through laboratory diagnostics. I'd like to introduce David here with his bio. So David received his bachelor's degree in chemistry from India University and obtained his MBA. He's the global business development manager of Double Engineering Company. He has 23 years of experience on the testing of insulating liquids and management of analytical laboratories. He has provided numerous technical presentations and published technical articles within the power industry. David is the Vice President of IEEE Member and Geographic Activities, MGA, member of IEEE Honor Society at Takapanu, while also serving as IEEE Board of Directors. David is member of the ASTM D27 Technical Committee on the Electrical Insulating Liquid and Gases. David is the past Executive Committee member of the Indiana American Chemical Society. So thank you very much, David, for being here for us today. Really appreciate your time. And we are sure that all the participants are going to have a lot to learn with you and to learn with your experience and on this topic. Thank you very much.
Thank you very much, and it's an honor to present at the YP Summit. So we're going to talk today about condition assessment of electrical equipment. We're going to focus on transformers today through lab testing. And what's absolutely important is no matter what the lab is, whether it's a commercial lab, a utility lab, that the sample of oil that they receive for testing is representative of what we call the bulk liquid insulation within that transformer. Over my years within the industry, I've seen grasshoppers, bugs, etc., all types of things within the sampling containers, but they were not actually in the oil that was within the transformer, and that can affect the test results that we generate. There's numerous guides that are available within our industry on how to obtain a proper oil sample. Doble, the company that I work for, we have a reference book. IEC has 2 different guides depending on what tests are going to be done. And then ASTM has ASTM D923, and that's predominantly what's used here in the United States and Canada. Now, why do we use a sampling container? We need to make sure that it contains enough oil for the test that's being requested. Usually we ask for twice the amount of oil. We also want to make sure it doesn't contaminate the sample, whether it's through leaching or water ingress issues. You also want to make sure that it shields the sample from external contamination. Sunlight has energy, so there's UV rays. You want to make sure that that oil is not degrading before it's tested in a lab, and of course prevents the loss or gains of materials tested for. These are examples. On the left-hand side are glass bottles. Those are used significantly in the US and Canada. In the middle are plastic bottles. Plastic bottles, regardless of their density, will allow for water ingress. So if you're taking an oil sample on a humid day in Denver or Istanbul, it's very important not to use these plastic bottles because of the issue of water ingress. On the right-hand side, I'm showing aluminum bottles, and they perform very well. This is a chart from a study that I co-authored a paper on, and you can see the HDPE, it stands for high density polyethylene. Those are the plastic bottles, and you can see at this study, we started about 5 parts per million, and we cranked up our humidity chamber in our laboratory, and you can see the significant amount of water that can get into the oil within a plastic bottle. That's why glass or aluminum sampling containers are recommended. This is an example of glass syringes. These are what's used to pull oil for the most important test that we're going to talk about, and that's DGA testing. This is a custom fit plunger and barrel that is guaranteed, once it's sampled correctly for 3 months, to be gas and airtight. Condition-based maintenance is the focus within our industry, within the Power and Energy Society. And through oil tests, we can make condition-based maintenance possible. When I started in this industry in '98, it was time-based. So they would take oil samples every year, every other year, depending on what the utilities' practices were. But now we've moved to a much more effective and cost-effective condition-based monitoring system. It allows us, most importantly, to identify incipient fault conditions. That could be overheating, that could be an electrical issue within a transformer. It allows us to find the issue before the unit fails or any other catastrophic issues occur. We can also identify long-term developing faults. We can tell if the oil or the cellulose insulation, which is in the windings, the center of the transformer, is wet. Water's bad, of course, in insulation systems, and that causes significant issues. And it also affects the aging life of the insulation. So we have various types of insulating liquids that are currently available globally. The one that's used the most is mineral oil, and that would be the focus of my talk today. But we have natural and synthetic esters, silicone oils, and then down below are chlorinated insulating fluids. Those aren't made anymore, but you still have some transformers filled with this liquid. So again, the most important test is called dissolved gas in oil. So what we do is we extract the gases out of the oil, we analyze them, we quantify them, and see what's present. And the most important gas we look at is acetylene. It takes the most energy, the highest temperature to form, and we'll talk about that. So from DGA, we can tell the following issues just from the test results and looking at trending. We can tell if it's partial discharge issue, overheating issues, whether it's low temperature, high temperature. Arcing, of course, in a transformer is the worst case scenario. That unit will fail unless it's remedied. We can tell if it's the breakdown of the paper. Maybe there's stray gassing, which is a chemistry reaction that takes place with different oils that aren't refined properly. Maybe there's contamination, etc. Now, when we talk about mineral oil, we call it a hydrocarbon oil, and that just means it contains a bunch of hydrogens and carbons. And you can see here on the purple, or it would be carbon, and the yellow would be hydrogens. So it can be in various different structures, whether it be paraffinic or aromatic, but at the end of the day, it contains hydrogens and carbon molecules. Now, how we do this test is we take the oil, we put it in the vial, which is in that lower left-hand picture, and in the top left picture, you can see a gas chromatogram shown, or a GC. And that oil is heated up, it's shaken for a period of time, and those gases that were dissolved in the oil will be liberated out, and they go to what we call a detector, and we get what we call here a chromatogram. Based on the retention time, or where the gases elude from the column to the detector, we know what gas is being analyzed. And then from proper calibrating procedures, we can tell based on the area under the curve what the equivalent part per million will be for each of the gases that are being analyzed. So again, when we talk about the breakdown of mineral oil, acetylene starts to be produced at about 700 degrees C. So that's a very high temperature hot spot, most likely caused from arcing. These are the four most common fault types that are found in transformers. The top left picture is arcing. That's the gassing pattern you expect to see, with acetylene being the key gas. In the top right is high temperature overheating of oil. Ethylene and ethane are the key gases there. And depending on what temperature and duration, you'll have various levels of the other gases. Bottom left, it would be partial discharge. We have carbon monoxide and hydrogen. And to the right, we have overheating of paper. Now, when the windings, this is a picture of the windings of a transformer, when they break down, they degrade from the cellulose structure and produce glucose. Glucose is not readily soluble in oil. However, it will break down and form carbon monoxide, carbon dioxide, and what we call furanic compounds, and we'll talk about that. But once we get the data, we need to know more information. How old is the transformer? We expect, of course, much lower levels of gases in a unit that's only 2 years old versus one that was made in the 1960s. Most importantly, what is the historical data showing? We could have some high levels of gases, but as long as they're stable and they're not actively rising, it is not indicative of an incipient fault condition. Our Standards Association with an IEEE came out with, in November 2019, an update to IEEE C57104. And what it did is it broke down the DGA results into 3 different statuses. Status 1 would be all gases are below the 90th percentile norms that they published. Status 2 would be all gases are below the 95th percentile norms and rates. However, any gases that were higher than the 95th percentile thresholds or normal gas generation rates, increased sampling frequency and additional actions were needed. So that unit could be in a status 2 or 3. The tests that we do on the oil, they're broken down into 3 different categories. On the left, the most common ones, they're diagnostic tests. In the middle, allows us to ascertain, can the oil in its current condition do its job, which is dissipation of heat from the windings where the heat's really generated and acting as a dielectric liquid. To the right are investigative tests, which would be tests that would be recommended should any of the other mentioned tests come out abnormal or do not make any sense. So for newly energized transformers, if it's a power transformer, we recommend all these tests be done. If it's just a distribution or smaller voltage class transformer, you recommend a DGA, furan, and water content just to establish a baseline reading for your unit. So you would want to do DGA, again, the most important test, all these durations, a day after energizing, a week, a month, 6 months, and a year. And why is that important? Because these transformers come with warranties, and you want to identify an issue with the transformer before that warranty ends to protect your investment. Oil quality tests on new transformers. The oil doesn't degrade quickly unless there's a leak or there's high levels of oxygen or a lot of heat that's available. So we just recommend a common screen package be done there. And then tests on in-service transformers. Every time you're going to pull a sample, we'd recommend you pull a syringe, which is where you get the oil for the DGA and the water content. And then other tests can be done on a routine basis, depending on, is it a sealed unit? Has there been any overheating issues? All those types of things. Another important test that we do in the laboratory is measure the amount of water that's dissolved in the oil. We do that via ASTM D1533. It's also called the Carl Fischer titration method, named after the famous German chemist that developed the test method. And what we do is we literally take the oil and we inject it into that red circular area, and it goes right into what we call the vessel solution. And the test equipment will measure the amount of micrograms of water that was measured. And from that, we can calculate the part per million of water dissolved in the oil. Why is water important? Well, we interpret water results similar to how we do with the weather and percent humidity. We need to look at the percent of water that is present relative to how much water that oil can hold at a given temperature. So for example, mineral oil can at 90 degrees C can hold up to 592 parts per million. However, at 10 degrees C, it can only hold 36 parts per million. So once you get, for example, at this 10 degrees C, once that water content of the oil approaches about 35, you're really saturated, you can get free water formation occur, which has incredibly low dielectric strength. This is the expression of the relative saturation and percentage. Again, we look at the concentration that we measure in the laboratory versus at the temperature that the time the oil sample is taken, how much water can that oil hold times 100. Here's 2 vials. They each contain 30 parts per million of water in the oil. However, the vial to the left, the temperature is 50 degrees C. That oil can hold significantly more water, so it's got a clear visual appearance and a low relative saturation of water and oil. The one on the right, the temperature's it's still 30 parts per million, but the temperature is only 0 degrees C. You can see it's got a cloudy appearance. It's got emulsified water, and down below at the bottom, if you could see it, you'd have free water formation. So when we continuously measure the amount of water in a transformer with an online monitor, you can see it changes over time. And that's because in a transformer, 99% of the water is typically in the paper, not in the oil. But over time, through heating and cooling, through changes in the loading of the transformer, you're going to see changes in the amount of water that's in the oil over time. But in this chart, if you were to draw a straight line through here, you see a slight raise in the temperature of the transformer, coupled with a slight raise in the water content in the paper, in the oil. Here's an example again of the windings that we're talking about here. Again, 99% of the paper approximately in a transformer is contained within the cellulose. And these transformers are designed to last about 20 to 30 years. You know, we see numerous samples where there's 60, 70-year-old transformers that are still well in service. The key is keeping temperature down, keeping the water content down, and oxygen. All of those add to the aging factors. And you can see here from this slide, the number one aging factor is heat, then in order is water and oxygen. Here's a zoomed in magnification of cellulose. It's a polysaccharide molecule. And you can see here it goes on for many chains. So when paper is brand new and it's put in a new transformer in a factory, it has about 1,000 to 1,300 of these chains. However, over time, these bonds become broken and the paper becomes weak and brittle. And that, at the end of the day, what causes the end of life for a transformer. So again, when that paper breaks down, it produces glucose. That's broken down, and that'll produce carbon monoxide, carbon dioxide. It'll produce acids. It'll produce furanic compounds, which we can relatively test the oil for, and then alcohols, methanol and ethanol, and that we test for very closely, and water. So based on these oil test results, what we want to do is be able to come up with a transformer health review or condition assessment. And a lot of companies will take the oil test results coupled with the offline electrical test results, testing that's done when the unit's taken offline, and give an overall transformer condition code. And what they try to do is make sure it's very clean and easy to understand. Red typically means warning or there's an issue, where green is typically acceptable, and they'll give a summary sheet so they don't have to look through hundreds of pages of data. They can quickly see which units require additional overseeing. And they also recommend that you use a software system that allows you to easily access and review your oil test results. That allows you a way to see the condition of your fleet in real time, and allows you to really do a deeper dive and look at those units that are causing more of an issue, etc. This is just an example. And then looking at the trending of your test results. And there's a graphical representation of DGA and water content results. Now, in the last few minutes that I have before we open it up to Q&A, let's go ahead and go over, I believe I have 3 case studies here. So here's a transformer. It's 24 years old. It's 115 kV, 40 MVA rated. The electrical test results showed that the Doble or power factor result was showing high, so that could be water issues. The DGA results showed a moderate high temperature or overheating of the oil. And it shows that the condition of the oil degraded over time, and the water content showed that the insulation is wet. However, the unit was lightly loaded, so it shouldn't be having overheating issues. But let's look at the data. Here's the DGA results. You can see that the gases are going up over time, but you can see with that June 24, 1994 sample, the gases dropped immediately. And that's because the utility degassed the oil. Once you get a significant amount of combustible gases present within a transformer, it can become a safety issue. The oil could catch on fire or the transformer could explode. So what they were doing here was monitoring it over time, waiting for a new transformer to arrive, and we're just trying to make it last. But you can see after each degassing, another one occurred November of 1999, and then of course another one in 2005 of June. These gases just continue to rise. So it's showing a clear indication with ethane going up of an overheating issue. As we look at the carbon oxide gases, carbon monoxide and carbon dioxide, again, they're affected by the degassing, but over time they're still going up. So that's an indication that the paper or the cellulose is breaking down. As we look at the gas generation rate from April 2001 to September 2005, you can see the total combustible generation rate approached about 1 part per million per day. Doesn't mean the transformer is going to fail tomorrow by any means, but this is a gas generation rate that you need to pay attention to. As we looked at the water content, the oil only had about 29 parts per million of water in it. The top oil temperature at the time of sampling was relatively low, of course, at 30 degrees C. However, at 30 degrees C, the relative saturation of water and oil is 35%, and that's high. We recommend anything below 15% would be acceptable. The amount of acid that was present in the oil was high. Another value of the oil, interfacial tension, was low, and the color was dark. So again, indications that the oil had aged from overheating, high oxygen that was present, and the water. So as they went in and looked at the transformer, you can see that significant discoloration with the main clamping top beam there. That was what was driving the overheating of the oil. So again, over time, it was a connection issue, but it accelerated the aging of the oil and generated gases because of that heat. What the utility did is they sealed up the unit after the inspections. They dried out the oil as best they can, doing a field dry out procedure. They reclaimed the oil to remove some of the acid and polar or ionic contaminants that got dissolved in the oil. And then they put the unit right back in service because it was needed for critical demand. This next data is from a utility here in the Midwest where I'm located. You can see everything was fine relative to the DGA results. However, in 2007, there was a tornado that came through and caused an event on the system. And now all of a sudden, we're generating elevated levels of hydrogen and methane, which are indicative of a partial discharge issue and or overheating of the oil. And you can see in 2008, they again degassed the oil. However, once they put that unit right back into service, you can see those gases with the red line, the total dissolved combustible gas, just shot up. And it was generating about 45 parts per million per day, which is incredibly high. And that unit would fail if not taken out of service by the utility. This last one is an instrument transformer. The utility called us and said, this unit's been in storage for 12 years. We're not really sure what's going on with it or why it was put in storage, but we'd like to put it in service. What are your thoughts? And of course, we responded with, let's do some testing. Let's see the condition of the oil and see if you can find any additional records. So after 12 years of storage, this is the DGA results. These are incredibly high values. So obviously, we did not recommend that this unit be put back into service. Also, from the furanic compound chart in the upper right-hand corner, we had incredibly high values in some of the key ones, especially 2-furfural. So that's an indication that the cellulose insulation in the paper and the windings were severely degraded within this transformer. With that, I would like to stop my presentation and open it up for any Q&A that we may have.
Thank you very much, David. It was like really fantastic presentation covering like all the technical aspects and showcases. We invite all the participants to drop any question in the chats. If you are watching from YouTube, Facebook, or LinkedIn, just drop your question in the chat. We already have one here. Do you use any kind of like AI on these studies, or they're just based on the data that you collect from the experiments?
It's a good question. There are utilities that are starting to use AI to develop an overall condition of a transformer based on numerous sets of inputs.
Okay, perfect. We have another question here. How do you monitor the different aspects of the oil in the transformer when it's working?
So you can take oil samples when a transformer is online. So the transformer is energized. You just have to take special safety precautions. They also have in our industry online monitors, and some of the tests that I discussed today via an online monitor, you can see this data in real time.
Fantastic. Another thing, like you have shown like some articles and like some test case as well. Is there any platform with this data available, these articles and studies?
So our response would be, we're going to be happy to share a copy of my presentation with all those that attend and are watching this webinar and maybe after the fact. And if there's additional questions, my contact information is provided.
Sounds great. Perfect. Right. Everyone, feel free to drop any question. Take advantage of the time here, David. Yeah, I have personally one question. You comment about the IEEE standards, right?
Yes.
for like usually young professionals, we are really interested on like how to get into the standards field. Do you have any experience on this area, or how IEEE is working on these standards as well?
Yeah, so IEEE is critical, and that's how I actually got involved with IEEE from a volunteer and member standpoint. So again, when I started in this industry, I was dealing with IEEE Standards Association. So within the Standards Association, the IEEE C57 dot, and it could be XXX, those standards focus on what results are good, what results are bad, what do you do in this scenario, etc. So IEC makes similar interpretation guides. IEC tends to be more used internationally in Europe especially, but again, very similar to what we do within IEEE. We produce these standards. They're also called interpretation guides to help. So you can be involved within PES with the Transformers Committee, and that's where these guides are developed and established and updated over time.
Perfect. Thank you very much. Right. Yeah, I think with that we can conclude our session. We have another session in a few minutes. So I just would like thank you very much, David, for your time to be here and share all this knowledge with the participants. It's really nice to have you in the YP Summit.
Thanks, Conrad. Thank you, everybody. Appreciate you attending.
Thank you. And for all the other attendees as well, I just would like to remind everyone, we have another session in a few minutes. So this session is a software training. If you register in the session, you're going to receive a link. And it's going to be a different link. It's not the same as this one right now, but just jump for another session. And after that, we have a Zoom meeting, which is a network session. So if you register again, you should have received your link for joining there. So thank you very much, everyone, for joining here today. We're really happy to have you all in the IEEE PES YP Summit. Thank you very much for the ones which joined it yesterday as well. And I hope to see you all in the next sessions, right? Okay, thank you very much. Really appreciate that.